Going into the last section of Module 4, Section 6, we're going to be dealing with what are called complex numbers. Now, a little background is when we see the radical, the square root of a -4, we know there are no two numbers that if we multiply them together are going to end up being a negative. So we say the square root of a -4 is not a real number. But mathematicians every once in a while in the past would find that they would get this. So they worked out a series of kinds of things they could do to work with this. And what they decided to come up with is to create a new category of numbers, which we're going to call imaginary numbers, that fit into a new higher category of numbers called complex numbers. So that's where we are right now. So let's do some definitions of what an imaginary number is. Well, what mathematicians did to solve this is divide this into the square root of a -1 times the square root of 4. And they defined the square root of -1 as the letter I. Lowercase letter I. So this would be I, the square root of 4, and we know the square root of 4 is 2. Now, they didn't usually write it this way. They would put the number first, and then they would put the I. So what is 2i? 2i is the square root of -4. So we will be doing some examples and going over some of the rules of how these imaginary numbers can be expressed. So in a sense, we're going to divide this into the square root of -1 times the square root of 3. So we'll put the I first, in this case, the square root of 3. Now, this is an acceptable way of writing it, but you could also put it this way, the square root of 3 and then the letter I. You just have to be careful you don't extend the radical sign over the letter I. So that's why this is often the preferred way to write it. So here, this will be the square root of -1 times the square root of 81. Square root of 81 is 9. 9i. Now, much of what we already study applies here. We're going to have this negative. We're going to take out the square root of -1 out of there. That's going to be I. And then we notice that the square root of 48 is actually the square root of 16 times the square root of 3 from an earlier lesson. So the square root of 16 is going to be a 4. We then include the I, and then the square root of 3. This is the usual way we write it, but that I could have come after the 3. Now, the nice thing about dealing with the letter I, it's treated just as it would any other variable. So in grouping it together, we could put them in like term columns. And I'm adding the 1 there. And we just add them up. 11 plus 5i. We have added, or in this case, and simplified. Now here again, we have 3 plus 2i, and we're asked to subtract Again, a negative sign in front of a parenthesis. What does that do when we take the parenthesis away? We change both signs. So this is a negative 6, and this becomes a positive 15i, and we just add them up. Now you might say, is it okay to do this mentally? Yes, but again, you want to ensure you get the correct answer. So again, this idea of lining like terms up and then making the sign change to both terms is important. Now, one case where the rules change just a little is when you're doing something like this. They're both under the radical, and you would think that negative times negative would give you a positive. Ordinarily it does, but when you're dealing with imaginary numbers, you can't do it that way. You have to convert this to its value, which is 3i, and this is going to be 7i. Now, what you do is you multiply these and you get 21i squared. I times I is I squared. Now, one of the most important things I need to tell you in this section is we never leave I squared as an I squared. We always convert the I squared to its value, which is a -1. So say it with me. What is I squared equal to? -1. One more time. I squared equals -1. Okay, and another important thing, when we write complex numbers, there is a formal way to write them. It's called A plus BI. Now, A is the real number, and the BI is the imaginary number. And when you have a real and an imaginary number together, that is a complex number. So this is the standard form of the complex number. And you could put a little star by that. So this one we did, and we realized where normally you might say that's the answer, because we never leave I square in an example. I squared is -1. So this becomes a -21 is the answer. Now notice if you did it the other way, then how we used to do it, negative times negative, would have made it a positive, and that's not the answer. So be very careful of this. So again, this is going to be I, and what is the square root of 8? Do you remember? We said that was 2, the square root of 2, because 8 is square root of 4 times 2. So we've taken out the square root of 4 is that. Now this is going to be minus I, the square root of 11. Now notice what happens here. 2i times I is 2i squared. 2 times 11 is the square root of 22. We never leave an I squared, so this will become a -2, the square root of 22. Now here there is a negative. Now 5 times 4, that's going to be a -20. I times I is I squared. But we never leave an I squared. That's a -1. So negative 1 times a negative 20 is a positive 20. So again, some basic skills of dealing with the letter I. Now in example D, we're going to distribute watching the signs, but anytime we get an I squared, we have to convert that to a negative 1. And then later we'll FOIL. But let's do this one. This is going to be a positive 12I, and this is going to be a negative 42I squared. But notice that I squared is a negative 1, so this will become a 12I plus 42. Now above they had said they want us to put our answers in standard form of the complex number. Is this in standard form? No. So if you put it in MATLAB like that, they're going to count it wrong. Now I'm able to give you some partial credit, because you did a lot of it right, just didn't put it in its proper form. And there's the correct way. Now when we FOIL this, and I'll do it very carefully with you, this is going to be a 12. This is going to be a negative 2I. This will be a positive 30I. And this is going to be a negative 5I squared. Okay, so this is going to be a 12. This is going to be a positive 28I. Now, I squared is a negative 1 times a negative 5 makes this a positive 5. We group our like terms. This is a 17 plus 28I. It's now in standard form, and that is the answer. Let's go on. Now, something from the past that we dealt with when we had something, let me write it over here, A plus B, and that doesn't look like A plus B. We said the conjugate of this was A minus B. That is, the terms would be the same, but the sign between them would be different. So we're asked to find, in this case, the imaginary conjugates of these terms. So if this is what we have, what would be the conjugate of this? Well, the first number would be the same, and the last number would be the same, but the sign in the middle would be the opposite sign. Now here where you have 10I, the superficial conjugate of 10I would actually be a negative 10I. But I will be showing you a shortcut of that a little later. Okay, so now what they want us to do is to multiply conjugates, imaginary conjugates. So remember, the middle terms cancel out when we multiply conjugates. So this will be a 4 minus 9, or 81 I should say. 9 times 9 is 81 I squared. But what did we say I squared was? Negative 1. So negative 1 times 81 makes this a positive 81. So the results of this is the number 85. Now we're going to use that here shortly as we do some manipulations. Now we're going to use the imaginary conjugate as we do some of these. And let me set it up so we can see it properly. So negative 3 plus 8i divided by 5 minus 4i. Now, they want our answers in standard form of complex numbers. And in standard form of complex numbers, you never have an imaginary number in the denominator. So we're looking for a technique to get rid of that imaginary number in the denominator. So it's a little bit like rationalizing the denominator, but what we do here is we take the conjugate of our denominator, which is going to be 5 plus 4i, 5 plus 4i. Now remember, this is something divided by the same thing. This is just a 1. But we're using the conjugate of our denominator. Now, 5 times 5 is 25 minus 16i squared. Now, since it's the conjugate, we don't get any middle terms. But now I have to FOIL this, and I guess I'll put it over here. So I'll put it up here, wherever I have room. Negative 3 times 5 is a negative 15. Now my outers, a negative 12i. My inners, a positive 40i. And my last, a positive 32 I squared. Now I can group that together a little bit. This is going to be a negative 15. This is going to be a positive 28i. And this will be a, remember, I squared is a negative 1. This will be a negative 32. Okay, so we've done some intermediate steps. Now, my denominator is going to be a negative 16 I squared, but this becomes a negative 1 times a negative makes this a positive 16. So my denominator here is going to be a 41. Now, my numerator, I have a negative 15 and a negative 32. That's going to be a negative 47 plus 28i. Now, theoretically, that's the answer. And that is correct so far. The only thing is not in this standard form. So if you put that in MATLAB, they may count it wrong, because they're telling you, put it in this form. So how do we do that? Well, we just separate them over the separate denominators. So this will be a negative 47 41st plus 28 over 41 and then we put the I out here in the numerator, but separately. So now this is officially in standard form. And I believe that's how they show it below too. Yes. Okay, let's do our letter E. Now for letter E, we said the official conjugate of this would be a negative 4i. But I have found through my work that we can just use a negative I as the conjugate. So it's a slight little difference, and you might say, why that? And the answer is, if you multiply this by a negative 4i, you get a large number. You just have to factor it out later. So this makes it a little easier to do. So 4i times negative I is a negative 4i squared. In fact, I can write it. Negative 4i squared. But what did we say I squared was? A negative 1. So this becomes a positive 4. Now, 4 times negative I is a negative 4i. 7i times negative I is a negative 7i squared. But what did we say was I squared? Negative 1. So this is going to become a positive 7 that we can put over here, minus 4i. Now, when we write this in standard form of complex numbers, this then becomes 7 over 4 minus 4i over 4. Now, theoretically, that would be satisfactory, but notice we could cancel out a common 4 here. So the official answer, 7/4 minus I, is what we get when we divide and simplify here. All right, let's go on to our last topic, which is powers of I. So let's give you a little background right over here, and you can take some notes on this. So we said I, by definition, equals I. That's an identity, a given. We also said that I squared was equal to a negative 1. We said that I to the third, or we are saying it, is actually I to the first times I to the second, which would give you I to the third, is a negative 1 times I, which gives you a negative I. And I to the fourth is actually I squared times I squared. That's negative 1 times negative 1, which will give you a positive 1. Now, as we continue this, we get I to the fifth, I to the sixth, I to the seventh, I to the eighth. But remember, this is all going to be I to the fourth, which we said is a 1, times I. So I to the fourth times I is I to the fifth. I to the fourth is a 1, so it's 1 times I. Now, I to the sixth would be I to the fourth times I to the second. I to the fourth is 1. I to the second is negative 1. Now, I to the seventh is I to the fourth times I to the third. We've defined I to the third as negative I. Now, I to the eighth is actually I to the fourth times I to the fourth. 1 times 1 is 1. So this pattern continues as you go up through the powers of I. So is there an easy way, if you know they have this sequence as we go through them, to figure out what these are when we simplify? And the answer is yes. For every I to the fourth you have in something, that is a 1. So you divide the exponents that you have into some power divisible by 4. So here we would have I to the 24th times I to the second. Now 24 is divisible by 4. So all of those powers of 4, which in this case would be I to the 4th raised to the 6th power. This is I to the 24th. Now 4 times 6 is 24. I to the 4th is 1. 1 to the 6th power is 1. So then you're left with this, I to the second. What is I to the second? Negative 1. So this answer here is a negative 1. How did we figure out? We took out all the I to the fourths out of that exponent. What we're left with is I to the second, and just applied it to this scale. And you'll have that in your notes. Now I to the 71st. Well, I did some research on this, and this is I to the 68th power, which is divisible by 4. So we're left with I to the third. So if we multiplied these, just add them up, we get 71. But since this is divisible by 4, all of this ends up as a 1. So we're left with 1 times I to the third, and we said I to the third is a negative I. So that's what this one is. Now here, this one's a little easier because I think it's easier to see. Something divisible by 4, well, that's 40. So all of this is just a 1 times I to the first. So letter C is just I. Now a twist to letter C would be something like this. So you might say, how do I do that? Well, I would do this part first, which we know is I, and then I would apply the negative sign. So this is equal to negative I. Now others might be something like this. I to the second raised to the third power. Well, what is I to the second? This is a negative 1. Raised to the third power is a negative 1. Now you could also have multiplied this by the powers here and get I to the 6th. And what did we say I to the 6th was? It's right over here, negative 1. So again, you've taken hopefully some good notes. You're going to work on your practice, your quiz-mes, get your mastery points, and take Chapter 4's test. Now remember, you can go back and take test again, and we count the better score toward your end of term grade. And when you finally do take your exit exam, super important is that you are showing the work of how you arrive at the answers. Now in some cases there may not be that much work, but you used your skills. What we ask students to do in that case is to write out in a short series of statements how they arrived at the answer. So we know you know how to get to the answer. Okay, that'll wind this up.